Okay, so it's time. If you want, we can start. Please, please, Tongyan, with the second lecture.
Okay, thanks. So yeah, good to see you all here again. This second lecture will go into some more detail about possible ways dark matter could interact in condensed matter systems. So I'll talk about dark matter electron interactions and dark matter phonon interactions. So to start off, let me remind everyone of this plot I showed yesterday, just as an example to illustrate why these condensed matter systems are so interesting for dark matter detection. So we have the sensitivity from nuclear recoils. These units this is a different axis than the usual WIMP recoil cross-section. This is dark matter electron cross-section. And this is actually a particular model that I'll talk about shortly. And you can compare nuclear recoils versus looking for electron excitations and phonon excitations in various solid state materials. And so that's why there's been so much interest and development in looking at different types of materials for this KeV to GeV dark matter mass range. And so last time I promised I would say a little bit more about what kind of models we're actually looking for. So I'll do that now. And what we covered last time was already the kinematics of why these kinds of excitations would be better. And now let's discuss a little bit the models that might live in this parameter space. In particular, you see this blue line. That's one example of a kind of thermal relic that is present. So the blue line is exactly where you want to live for the couplings to get the thermal relic through a dark photon mediator. All right, and as always, feel free to interrupt with any questions, comments. All right, so let me say a little bit about this dark photon mediator scenario that gives rise to that blue line. So the place it usually comes from ultimately is some sort of kinetic mixing between a dark photon, so that's the prime, with hypercharge. And there might be some mass term for the dark photon, the A prime. And this is something that is very easily generated. So this is a epsilon parameter. It's very easily generated if you have some heavy particles. Just call them F. And they might be charged under both the new U1 and the existing U1. And so through this kind of diagram, then you'll typically get small numbers through this loop diagram. And so you can easily get some sort of small number for this epsilon y, this kinetic mixing here. And so it's very natural to think about these dark photons. And for our purposes, we're talking about sub-GeV dark matter. We're really focusing on low mass mediators as well. So we're really focusing on sub-GeV A primes as well. And so the thing we'll actually focus on is you can just focus on the mixing, kinetic mixing with the standard model photon. For our purposes, we won't have to talk about the Z mixing part. And so to treat this, there's two different bases that are often used. One, you can keep this as it is, but I'm going to go to a different basis by rotating away this kinetic mixing. So I can do that by taking standard model photon to be photon plus a small mixture of this dark photon. And the reason we do that is because the dark photon already has a mass term. So if we were to do this rotation on the dark photon, we would get mass mixing terms. Whereas we start off knowing that the standard model photon does not have a mass. And so we perform this mixing that gets rid of this kinetic mixing term. And we're instead left with coupling I mentioned yesterday, which is coupling of the dark photon with all the standard model stuff, the electromagnetic stuff. And so that leads to the kind of interaction that I drew before, which is that this provides a very good mediator for freeze out, freeze in direct detection. So for instance, this is a process that's possible in the early universe, and couplings we'll consider usually G chi and epsilon E. If this happens, if this process is in equilibrium, that would allow for dark matter freeze out. And there's also freeze in, the line I just showed, which is possibility if this diagram only happens in, in one direction, which is the direction of producing dark matter out of the thermal bath. So dark matter is not in equilibrium. You just have very rare interactions that are occurring in the standard model thermal bath, where occasionally E plus minus will annihilate to the dark matter. And you can produce the right amount of dark matter in this way through some, the combination of couplings is about 10 to the minus 10, so much smaller. And this Ma prime is pretty light. The dark photon is pretty light. Okay, so it's possible to have both the freeze out, freeze in scenarios, and I'll show those both on these kinds of cross-section plots. And if we have this coupling, then dark matter will source a potential in materials. So this is basically just a Coulomb or Yukawa potential if we include the mass, and I'll write it in Fourier space. So you just get a Q squared plus Ma squared. So normally when we're talking about scattering events, we're used to thinking of like say, computing a 2-to-2 scattering process or 2-to-2 interaction process, kind of like this. But when it comes to treating the dark matter and the materials, this kind of diagram, while it's useful, can lead to, it can be misleading. So another way to think of things is by writing down the potential sourced by the dark matter and figuring out how this potential perturbs the material. And the reason is because when we're dealing with a material, we're not necessarily dealing, it's not always easy to think of the material as just a collection of individual particles that the dark matter can scatter off of one by one. We're really thinking of the material, which is has a lot of interacting components all responding at once. And so that's why I'm treating this in the language of what's the potential of the dark matter as it's passing through this material. Okay, so mainly I'll work with, one of the ones I'll work with is this dark photon example. Another case that's often considered just to cover our basis is what if there's no such electron coupling and we just have a leptophobic mediator? So this would be a scalar and primarily couples to nucleons. And similar, we would have a potential sourced by this dark matter as well. Where now I only sum over the ions in the material. So I meant the ions, where I'm treating that solid state material as basically ions plus electrons. One other thing to mention about the kind of interaction we'll look at is that there's usually two limits taken for this potential. So we don't, of course, a priori know what the dark photon mass is, different models of different masses, in case you can do a study for a particular model, but usually we'll take two limits, the massless mediator limit. So that means MA prime is much less than KeV. Doesn't have to be massless, but as long as it's much less than KeV, then its presence in this potential can be neglected. And so we'll see that's because the typical momentum transfers are either going to be M chi V0 or alpha ME. And both of these, well, this is going to be greater than order KeV. And this one can actually be as low as, say, a few EV. So really this maybe should be stronger, much less than EV. And the other limit is the massive mediator limit. And usually this might be of order the dark matter mass. And when that happens, typically Q, basically the massive mediator limit is where Q is much less than MA prime. So we consider those kinds of limits for our scattering potential usually. So basically the first one is like a Coulomb potential from the dark matter, and the second one is like a contact interaction. All right, so I've introduced now two possible mediators and the kinds of external potentials that they introduce. And so let me sketch out now how the scattering rate is computed in the material. And I'll draw an analogy with the calculations that we looked at yesterday for dark matter nucleus scattering. So for dark matter nucleus scattering, we found that the leading operator looked for vector interactions had this coupled basically to the one operator, which means coupling to the nucleon number density. And the same is true now. We're also coupling to the number density. So before it was rho n, and we're summing over nucleons. And now we're coupling to rho e, which is the electron number density, as well as possibly rho I, which is the ion number density. And it's appropriate to use to think about these instead of nucleons or more individual particles, especially for low Q, so low momentum transfer. So to give you an idea, the interparticle spacing in materials is order angstrom, which corresponds to momentum transfers of order keV when we do 1 over angstrom. On the other hand, when we were looking at dark matter nucleus scattering, we were looking at much larger momentum transfers. That was more of order MeV or even 100 MeV. And so there, it's really appropriate to deal with individual nuclei and even go as far as the nucleons within the nucleus, right? Because once you get to pretty high momentum transfer at 100 MeV, we saw that you're not probing the nucleus as a whole coherently. There was a form factor, the Helm form factor, which led to some suppression in the coupling once we get to really high momentum transfers, and you no longer have this being just the sum of all the nucleons squared, but you're probing the structure. So similarly for the solid state systems, once we get to momentum transfers of order keV, which is definitely relevant for light dark matter, because that's comparable to the interparticle spacing, we can't really think about probing just a single electron or a single ion in the material. We have to sum up all the electrons and ions in our electron density operator and our ion density operator. And we need to compute a different kind of form factor, which will be called the dynamic structure factor. Okay, so to remind you, for the Helm form factor, we just computed it with the nucleon number density operator. And in particular, we computed it with the same initial and final state because we're just recoiling against the nucleus as a whole, and we're not exciting any internal states. Now for the solid state system, we compute a similar density operator expectation value, but we we have different initial and final states corresponding to, say, we might start with a ground state of a system at 0 temperature, and then we might create some excitations with some energy, with some difference in energy omega. So again, this is just like, this is just perturbation treating our external potential as some perturbation to this, this whole system, and here computing some rate to produce excitations. Okay, so I'll just give you the form of the total rate, and it looks very similar to when we wrote it down for dark matter nucleus scattering. The dark matter number density here. This is the target mass density, and it just replaces the number of targets before, so we can still talk about the exposure in mass times time. As before, we have the dark matter velocity distribution in our halo, and some fiducial cross-section. This is the reduced mass of the dark matter, either with the electron or the nucleon. So we always typically put our overall form factors here. And then we want to integrate over the possible phase space of the excitations. So last time I emphasized that we treat this in energy deposition omega and momentum transfer q. There's a dark matter mediator form factor here, which I'll explain in just a moment. And that's the dynamic structure factor that I just introduced, which is like the form factor for the material. And this is just energy conservation, saying that dark matter deposits energy omega. Okay, so that's going to be the same as that relationship between omega and q that I introduced last time. Okay, so this is relatively straightforward in that, okay, we packaged all the material properties inside this one function, the dynamic structure factor, and everything else here is either the astrophysics of the dark matter, density and velocity distribution, or various particle physics quantities that we can compute, namely this fiducial cross-section and this mediator form factor. And so let me just define those more explicitly. So let me just do the electron case. So this combination in front, the cross-section over the reduced mass, is just the combination of couplings, for instance, for a dark photon. And I call it a fiducial cross-section because it's defined at some reference momentum transfer. Okay, so this is basically just that strength of the potential. And it's defined at a reference cross-section just so we can compare, and the actual momentum dependence of the potential is then absorbed into this mediator form factor. Okay, so the dark photon mass dependence of the potential I absorb into this mediator form factor, and this part is just pulled out in order to define the cross section. Okay, so basically it looks very similar to calculating dark matter nucleus scattering, just with essentially with the replacement of these form factors, the nuclear form factors with this. So in today's lecture, I wanted to focus on giving some intuition and sense of what this form factor looks like in various materials, and how that compares with the allowed phase space for light dark matter scattering. Are there any questions so far that on the more dark matter model side? Okay, well, we can always return to this later. So now I want to get started into thinking about dark matter electron scattering and computing that structure factor. So let me recap a little bit about electrons. I went fast last time at the end because we were out of time, and I'd introduced this band structure plot, which if you start looking into the literature and some of this thing, you might see this a lot. So I want to make sure we go over it a little bit more. So as I said, one of the important elementary excitations in solid state materials are electrons, and they're not exactly electron particles, but they're called electron quasi-particles. So there's something that's not exactly an electron, but they behave a lot like an electron in that they have the same charge, they're a fermion, but they have a really funny dispersion. So we can almost think of them as having a different kind of mass. It's called a band mass. And so the toy model of where this usually starts comes from basically looking at the electron wave function in a periodic potential. So remember, there's a theorem called Bloch's theorem, which says that you can write the solution to Schrodinger's equation in this periodic potential most generally as some phase factor times another periodic function. And furthermore, these solutions, the set of all solutions, will be equivalent if you kind of take this label K and change it to K plus a vector G. If GA is equal to 2 pi. And I'm doing it in 1D, but of course this will be in 3D. You have a dot product of G dot some lattice vector. So because of this equivalency, usually the spectrum of solutions of eigenstates is shown inside the first, what's called the first Brillouin zone. So for instance, for just a 1D periodic lattice, K would be in minus pi over A to pi over A. So you would just show the spectrum of eigenstates in a particular K range. And it's a simple, the Brillouin zone is simple for this 1D periodic lattice. In a crystal, we have a three-dimensional structure, and it becomes a little bit more complicated. And so what's shown here is basically, if you imagine this 1D thing gets replaced with a 3-dimensional object. And this is a path going in that 3-dimensional space, k-space. So this is basically showing momentum on this x-axis, where momentum really means the label of these solutions. But you can think of it roughly as an electron crystal momentum. And these labels are just particular labels. There's a convention for them, for what they mean in terms of momentum. I don't even remember them. The one that's always useful to remember is gamma. Gamma is always k = 0. Okay, so there's a lot of stuff going on, but let's we can simplify a little bit. And if we look near gamma = 0, what you'll see is there is actually this quadratic dispersion here, which is basically the beginnings of a k²/2m dispersion, which you would expect for free electrons. And if you were to continue that, if you didn't do this cutting off of the momentum space, you would just keep going like this, right? But instead it's folded over and it's mapped back into these lines here through the equivalence shown here. And so then the way we read this is you can think of this boundary here as roughly where the momentum becomes pi over the lattice spacing A, which is typically going to be around keV. So you find the gamma point and kind of just imagine that this axis now is going from 0 to keV in momentum. And then you can read now the energy eigenstates going up, which will be something like a free electron, which looks like down here, but then get more and more distorted, as you can see, depending on the material. And these other points are just other finite momentum points. We won't really look too much at this region. One important point is this dashed line here. This is the Fermi energy for this material, which is silicon. So that means all of the eigenstates are filled up to that energy. You can imagine this these bands really as having a discrete number of eigenstates. So really, it's like this. And as we fill it up with all of the electrons in the material, it goes all the way up to here. So everything below is going to be the occupied states, and everything above are available states we could excite to. And importantly, there's a gap here. So the highest occupied one is around here, and the lowest available one is here. So this has a gap of around 1 eV. So when we talk about dark matter excitations in this material, then we can think about specifically removing, for instance, an electron from here and say exciting it to some available eigenstate here. Actually, let me draw that better, because so we can remove it. And so the horizontal motion we make, or the horizontal part, will basically be the momentum transfer, and the vertical part will be the energy deposition. So this is a typical example of a semiconductor with the, like I said, electron volt gaps. And that's going to allow us to probe dark matter as light as 1 MeV. There are some other possibilities for where this EF, this Fermi energy, might be located. So if it's down here, let's say EF were down here, that would be metal. Because there's basically no gap from taking an occupied state to an excited state. Another possibility is if we had an insulator. That would be pretty similar to this band structure, but the gap would basically increase to about 10 EV. So there's no exact boundary, but if you basically moved all the bands above, unoccupied bands above, up by like 9 EV, that would be like an insulator. Okay, and if we move the Fermi energy below, that's a metal with 0 gap. Okay, and so that flexibility gives a lot of options when you're considering different materials for dark matter scattering. But let's focus on the silicon example. And let me show you now just some schematic of how the experiment might actually go. So these are schematics from real experiments. As I said, what we imagine happening when dark matter comes in is we take this occupied electron and we excite it to some state, the electron in the occupied state to some available eigenstate. And so what happens after we excite that electron? That's a somewhat complicated process because now that electron, so we have the excited electron, can decay to other electrons. So it can decay to some state there. That one could decay here. And so there's a kind of cascade process where the amount of energy you deposit will lead to one electron, but then that'll cascade into a few more electrons. And so roughly speaking, you'll get out a number of electrons at the end of this cascade, which is omega over about 3 electron volts, depending on the material. Maybe higher in insulators. But for silicon, it's around 3 eV. And so that's the number of electrons you might observe. And so if we look on the right, how would we observe that? Now we can take this number of final electrons in the cascade, and in the Domik and Sensei experiments, what we have is a silicon CCD, and that's this blue region. And when we have one of these observed electrons, you'll have an electron in a hole. And if there's a bias voltage, then it'll drift the electron to one side and the hole to another side. The hole is just, sorry, the unoccupied state. Okay, but more importantly, let's just say we drift the electron with this bias voltage. So that's just the operation principle of a CCD. And what Domik and Sensei experiments are doing are using particularly thick CCDs that we have enough mass, and also and a bunch of basically treating them as dark matter detectors, where we're taking a picture of electron ionization events that happened. So the bottom plot is showing basically a pixel. Well, it's not a pixel, it's a bunch of pixels in a CCD. And instead of usual CCDs taking pictures, if you cover it for a long time and you wait, you get a long exposure of the CCD in the dark. And for instance, this one pixel here shows, has a measured charge of exactly 1 electron being produced. Everything else is 0. And through this, you would say I have an event with 1 electron, which would correspond to about 1 to 3 eV. So it can be as low as the band gap, but it could be as high as 3. Okay, so these experiments are running, and I'll show you some of their results. But already from here, you can see they have some really nice techniques to basically reduce noise and see just that spot from that single electron type events, very low energy events. Okay, so I think before the break, I'll say a little bit more about the dynamic structure factor in materials, and then we'll continue with the electron scattering after. Okay, yeah, I'll try to finish the electron scattering before the break then. All right, so to make this a little bit more concrete, I like to use the example of the hydrogen atom, just as a case where you can compute things without having to go into all the band structure I've been talking about. So to remind you, the thing that we care about, this dynamic structure factor, let's write it again. It's just the expectation value of this density operator. And the thing that can be quite complicated is identifying what the initial and final states are in a many-body system. But as a warm-up, we can simplify things with the hydrogen atom and just take, for instance, for hydrogen atom is simple. We just have 1 electron, and we'll take that to be, separate hydrogen atoms as our target. So I will just be the ground state of hydrogen. So it'll be proportional to e to the minus r over Bohr radius. And in this example, I'm just going to take the outgoing states to be free outgoing electron states. So K prime is the outgoing wave. That is the momentum of the outgoing wave. And because there's just 1 electron, then I don't have to do any sum. J is equal to 1, and I can compute that matrix element directly. And so that's what's shown in the plot on the right, basically computing this matrix element and summing and including this sum over final states with a delta function, which anyway just turns into a factor. So this is the log of the dynamic structure factor for hydrogen. Okay, so what we see is one, that scattering is going to be peaked in the 0 to 5 keV region, so around 5 keV or less. And so that justifies what I was saying earlier, that the typical momentum transfer that we're looking at in scattering off of electrons is going to be of order 1 over the Bohr radius, or alpha ME, or 5, which is about 5 keV. And the typical energy is 20 eV or below. So note that this is cut off at 13.6 eV, which is the gap for ionizations. And then the rate is kind of peaked just above that, around 20 eV. Okay, so this is the basically, this is showing us how easy it is to excite the material in a given Q and omega. And then we have to compare that now with what is the Q and omega available for dark matter scattering. So that depends on the mass. But if we take a momentum of 10 keV, so if Q is 10 keV, then we expect that the corresponding omega is going to be less than Q times the dark matter velocity, which is 10 going to be 10 eV or so. Well, it'll be up to 20 eV, because then it wouldn't show in the plot. So really, if we looked at dark matter scattering, it would actually give us a parabola that's very low down here. So probably should change the axes here, but basically you're not really scattering, you're not really able to access any of the stuff up here. For dark matter scattering, remember we had a parabola, and it's going to be all the way down here, kind of that large momentum and low, relatively low energies down there. Okay, so this kind of gives some intuition for how you might even think about comparing different materials and looking for a material that would be optimal for dark matter electron scattering. Basically, you want to look at this structure factor and see, what kinds of materials give you plenty of signal down here. Let me show you then the result for the silicon semiconductor. So that's this plot, and it actually has quite a few features in common with the hydrogen atom one. You can explain a lot of it similarly. One is you can see that the typical momentum transfers here, where we get the most weight, is similar. It's going to be order 5 keV, a little less. We get similar momentum transfers, and again, that's basically coming from the fact that when we look at the electrons in the material, that sets the scale for the momentum of the electrons and their wave functions and so on. So that's always going to appear as a typical scale, or that's generally going to appear as a typical scale. Won't say it for every single material. In this case, because the band gap, the delta E, is greater than 1 eV, the structure factor, the dynamic structure factor, extends to much lower energies. So it does go all the way down to 1 eV, and you can see a little bit of white region here, and that's basically the part that's excluded from 0 to 1 eV due to the band gap. So that's already a lot better. And if we were to draw that parabola for dark matter scattering, it would look something like this. So you're still not quite reaching the most optimal part of the structure factor, but you are doing a lot better with a semiconductor down here. Okay, and there are various subtleties in calculating the structure factor. So these initial and final states are not, you cannot just use the block states that I mentioned. As shown in our some recent work, which I've cited below, we've shown that these are really many body states. And if you do that, it introduces some additional effects, basically screening in the material, as you're exciting the material as a whole. So it's a many body effect. In any case, I won't go into that other than to comment. You can't just use the block states in the initial and final states when thinking about this dynamical structure factor. You have to count for various many body things. Okay, so given that, here's a comparison of different kinds of materials that have been studied in the literature so far. So basically, we've been looking at different structure factors, and now I'll show you how that translates into a reach in the dark matter electron scattering cross-section plane. So dark matter mass and electron cross-section. So first thing to note is the left plot is the massless mediator limit I mentioned. So that was the MA prime, that's just an EV. And this is the massive mediator, so MA prime is M chi. And in each of the plots, I have that kind of thick bluish line. So those are interesting thermal relic lines. So those are free, that's the freeze in line. And I also have freeze out over on the right side. The two different lines are for scalar versus fermion. Okay, and now all the different colorful lines are projections for if you had a kilogram of material and you waited a year and you had very low background, what's the best you could do in different materials? So starting on the left, if you have an insulator, which my example here, if you have an insulator like diamond, or maybe the hydrogen atom, that would give you something like this yellow curve. So that will have the highest threshold, delta E of 10 electron volts. So it will only go down to order few MeV in dark matter mass. And these next two lines, those two are silicon and germanium semiconductors. So that corresponds to lowering your energy threshold to about an EV. So you can basically significantly improve the region around 1 MeV by lowering the threshold. And then you can ask, going for in the future, what if we could have even lower threshold detectors? So the darker lines show two proposed possibilities. One is to consider a metal, and that's this line. Now, rather than a metal, the original proposal was to consider the metal in the superconducting phase, which is better in terms of detecting the actual excitations that you produce. But for this discussion, it's not too important. I'll just, you can just think of it basically as a metal. So when you have a metal, then the gap basically goes to 0. The experiment might not be able to go to 0. So I've put thresholds of 10 millieV and 100 millieV. So as you lower the gap, you can keep doing better and better, particularly for this massless mediator case, because remember, it's like a Coulomb potential, which is highly peaked at low momentum transfers. And so it's really beneficial to keep going lower. And then this one is another example, kind of exotic, more exotic material, the Dirac material, which is something which also has a really low threshold to excitations. Here's about 10 millieV. So there are a bunch of existing experiments already with these kinds of energy thresholds. And then in the future, we can explore more novel materials and get to this dark matter mass range. Okay, and for the massive mediator, the advantages of going to low threshold, there aren't quite as many. So all of the lines basically are cutting off at around 1 MeV. It's hard to go below. But the model space is also not extending to sub MeV. Okay, so one quick comment about solid state materials is also that they allow for directional detection. So in this graphic, what you see is there's a particular crystal, and the structure of the crystal actually depends on which direction the dark matter is coming from and how you're exciting it. And so as the Earth rotates, this is the Earth axis of rotation, t equals 0, you'll look at the crystal in one direction. Half a day later, this will have rotated around, and you're basically probing the crystal in a different direction. And you can actually get a modulation in the rate, which for some materials is quite large. So in this example, it goes from below 1 all the way up to 3. So it can be factor of 3 change in rate throughout the day. So if you were to observe any signal, then you could try to use that to distinguish a dark matter origin, which is very important because with electron recoils, we don't have a way, we don't currently have ways to distinguish, whether electron recoils are coming from some background or from dark matter, unless we use the spectrum and maybe this effect where it's modulating throughout the day in a particular way. Okay, so I have one slide about experiments, but I think since I'm running into the hour, I'm going to stop there for this first section and we can take a break.
Okay, great. So we'll resume at 04 or 05. There's a question though first. Would you like to answer it?
Sure.
Okay, the first one, it's very quick. When you say Dirac material, you mean something that has, the cone-like dispersion, like graphene or something? Okay.
Yeah.
And the second, about the plot with the reach you showed. So this one, yeah. So you said, provided there is low enough background. Does this mean that, this is a plot, like one of those very optimistic plots that, as a theorist you like to do, but there is not much input from experimentalists or?
Right, this is just I would call this more of a materials comparison. So it's what's the best you could do comparing these materials. But of course, realistically, yeah, you have to consider lots of backgrounds, which might be more materials dependent. But yeah, this is more of a, what's the best you could do with a material just to sort of guide your thinking about different materials. So yeah, indeed, these are optimistic with 0 background assumptions, very optimistic, yeah.
Okay, I see no other questions. So we have a break and resume in 5 minutes. Shall we restart? Please.
Okay, thanks. All right, so forgot one last thing I wanted to show about dark matter electron scattering, which are actual experimental results. So that's summarized in this plot. It's the same dark matter electron scattering cross-section. And now you see that there are actually tons of experimental results in this regime with pretty low thresholds. So there's Domik and Sensei here are the CCD experiments I mentioned with silicon CCDs. And they have fairly small exposures so far, order 1 to 200 gram days. And they're also currently dealing with some, well, this one is actually not even that far below the surface, so there's lots of potential backgrounds. But you can see, even though the exposures are still relatively small right now, it's not even that far from the interesting cosmological benchmark I mentioned. So this will be pretty exciting to follow in the next few years. Okay, so that's it for dark matter electron scattering then. And in the remaining time, I was going to briefly cover dark matter phonon excitations. I also have lots of extra references I can share later if you're interested. Okay, so dark matter phonon excitations are really going to be for sub-MeV dark matter. And the reason for that is related to the energy scales of phonons. So let me step back for a moment and just recap what I covered last time, maybe expand on that a little bit about what phonons are. So in a solid state material, we'll have some regular arrangement of the atoms in their lowest energy state, so some equilibrium positions. And phonons are the collective displacements from the equilibrium position. So you can talk about the position of some atom in a lattice at a particular lattice site. So there might be a crystal like this one where you have two different types of ions at a lattice site, and you would expand about those positions. So this is just a vector telling you which lattice site, the equilibrium positions, plus U is the displacement. So what happens next is basically just a harmonic oscillator. There's a potential energy for which you can calculate for all the positions. And so like any equilibrium system, we can expand about it to second order in the displacements. That'll be the leading correction if the ions are displaced. So that'll just be a harmonic oscillator. And if you recall from a 1D harmonic oscillator, you have the position being related to creation and annihilation operators. In solid state material, we would have the displacements also being a sum over creation and annihilation operators. The difference is that we have a continuum of energy modes, so we have to sum over all omegas. Okay, so we have, these are basically the phonon dispersions, and we associate these creation operators with creating phonons, single phonon. And the E's are basically some eigenvector, some overall normalization for the phonon. It's not too important. So that's basically it for the for phonons. You basically take the eigenmodes of the displacement, and when we quantize it, we turn it into we write it in terms of phonon creation operators. And similar to the electron band structures, we'll have some sort of phonon band structure. And there are different types of phonons that you could have. As I mentioned, there's the acoustic phonons, which have a linear dispersion. They're like the Goldstone mode. And there's also optical phonons, which are gapped, and they typically have energy of around, you can see here, this one is around 35 millieV. And they can go higher up to 100 millieV. But it's really because of those energies that we focus on sub-MeV dark matter, because these are pretty low energy excitations. So they're likely to be more optimal for sub-MeV dark matter. Also on here, this is a log-log plot, but basically this is the same parabola I've been showing in the energy transfer and momentum space for dark matter scattering. And so you can see, this is dark matter scattering for a particular mass. I think it was 35 MeV. And so you can see these optical phonons live right in the middle of this phase space where you want them to. And that's why phonons are also a very exciting direction to go. They're right in the middle here. The acoustic ones aren't quite as good because they kind of live in the corner of the available phase space. Okay, so this is basically a similar plot. There's the same parabola where you have allowed scattering. And here I'm just indicating that for different types of materials, you have different possible energies for those optical phonons, but they'll live somewhere in here. And the acoustic ones are down here. And this red line is actually Q squared over 2 Mn, which you see is pretty much awful in this mass range. And schematically, how would we detect one of these phonons being produced? So let's say I did want to excite an optical phonon, or let's say dark matter came and excited an optical phonon. That will come in. So I have a phonon in some material. Here, this is gallium arsenide. Again, we don't detect the primary excitation. It will shower and cascade. So there will be lots of other phonons being produced, lower energy phonons, and they might even bounce off the surface and bounce around. And the proposal is that the surface of this cube would be instrumented with these collection fins and TS's. So what does that mean? The blue region is a region where the phonons can be collected. So that means as these lower energy phonons are bouncing around inside, some of them might hit this collection fin, this blue region, and be absorbed there. And then the purple regions are basically the calorimeter part, or the bolometer part, where the energy of the phonons in these collection fins is measured. So the idea is if you can cover this efficiently, then you can measure most of the energy deposited from the single optical phonon, even though you're not detecting the original phonon itself. And these, of course, have to be very low threshold, very sensitive. For instance, 10 millieV threshold. So I want to say a little bit about the dynamic structure factor for phonon excitations. It's very similar to what we just talked about, but now we're considering the coupling of the dark matter with the ions in this lattice. So here's my example of a lattice again with different ions in a periodic lattice. And the dark matter will have some different effective coupling with each of them. And again, we want to sum over all of them weighted by U the IQR. So the way the phonons come into play is through this quantized displacement field. So very schematically, if we have this matrix element, we can take our initial state to be one in which the system is in its ground state and there's no excitation, so just vacuum, no phonons. And we can take our final one to be basically one phonon, could be one phonon like this. We could also even consider two phonon states. And then this matrix element is not hard to compute if you've determined these phonon dispersions and the modes, eigenmodes I mentioned, because you just have to expand this. So you'll get one, which doesn't, this is basically no scattering, but you also get a contribution of IQ.U in there. And you can see that will give us a matrix element with the one phonon state. And there's also, you could also get, well, you can also get two phonon terms, which won't worry about, two phonon. So this structure factor, dynamic structure factor, then we can, once we have some methods to compute this, which will come from the condensed matter side, we can directly compute a one phonon form factor, two phonon, and so on. Another one interesting thing about the phonons is that which phonons get excited depends on how the dark matter couples to the various ions in the material. Oh, sorry, I didn't quite get there yet. Actually, I'm going to skip that comment. All right, so given this, given this one phonon structure factor, we can do a similar kind of comparison, materials comparison. And this is basically the previous plot I showed, but now I've added on the phonon bits. So these are different optimal reach curves for materials which have optical phonons that can be excited. So these are all with optical phonons. And what we see is that these materials with phonon excitation are particularly interesting because they're even stronger than the ones you would get from electron scattering, which are the ones shown above. And I think that can be understood by going back to this plot I've shown several times of the available phase space for dark matter scattering, and the fact that these optical phonons kind of live more optimally in the available phase space, whereas when we studied the structure factor for the electron scattering, we weren't really hitting the peak of the structure factor with the kinematics of dark matter scattering. So as a result, we get some few orders of magnitude here. In addition, you could also look at different types of mediators. And as I said, for different types of mediators, you actually excite different types of phonons. That's an advantage because you can then again, use that complementarity to, you can use that fact to try to distinguish whether you're looking at which type of dark matter model you were looking at if you were to detect a signal. So for a scalar mediator, you would actually preferentially excite acoustic phonons, which is how these curves here were obtained by computing acoustic phonon excitations. And these lines up here are actually the nuclear recoil reach with somewhat higher threshold. So this extends it down to sub-MeV with phonons. Similarly here, we're focusing on the sub-MeV mass range. Again, for a solid state material, we can have a very anisotropic material where the energy of the phonons and the eigenmodes depends on the direction that we're looking in. So this is the same diagram, and now you can compute how much does the rate change over one day for phonon excitations, and you see similar, it's a bit smaller here, but depending on the dark matter mass, you can get sizable daily modulations, which again helps you try to figure out if some signal was coming from dark matter. So let me actually go back and write this single phonon structure factor down. So these were the phonon eigenmodes and the energies appearing here. And so this structure factor is a little harder to show because it basically is a delta function on top of wherever the phonons are. So that's why I'm not showing any plots. But you'll get different weights on different phonons depending on how the eigenmodes look in a particular material. So this will be a material dependent eigenmode, which just tells you how the different ions are oscillating. And that's, again, powerful because you can use that information along with the coupling to figure out, to try to determine if your signal is from dark matter, or maybe combine different materials to figure out the dark matter model or to figure out the origin of a signal. And so here's a schematic from the Harold and Spice experiments showing a plan for using, in particular, sapphire and gallium arsenide and looking for the phonons being produced. You can ignore this photon part, that's a different signal. So these are both materials with the optical phonons, and you can see the collection fins and the TSs instrumented on the surfaces. Another idea that's being proposed recently is to use liquid helium, particular superfluid helium, which also has phonon modes. This is a liquid, so it's a little bit different, but the basic ideas are similar in that there are something similar to acoustic phonons, and you can produce them and they will bounce around, and then you can try to measure the total energy being deposited. So these are currently being developed, all based on phonon detection. Okay, and there's a lot more to say about that, but I'll just leave the references later if you want. And come to my last couple of slides. So to summarize, there's a lot of potential for exploration for different types of novel materials and novel material excitations in here. And one thing I hope that you come away with is that when we think about the rate in these materials, we can kind of absorb all the material dependent effects into one quantity called the dynamic structure factor. And it's the analog of the form factor when we're talking about high energy scattering, for instance, or higher energy, or for nuclear recoils. So it's a low energy form factor in terms of momentum and energy that we can use. If we know it, then we can easily figure out how the material responds to this passing dark matter and its potential. And hopefully I've given you a sense of why so many different materials are considered. There's lots of things I wasn't able to discuss, but hopefully that gives you a sense of why that's a growing and important direction for these sub-GeV dark matter searches. And that's it. I'm well over time. I'm well under time, which is good.
All right. Thank you very much. Thank you very much. All right. So we have time for questions. Wei, please.
Hi, Tongyan. Thanks for the lecture. So I have a question regarding the